let's start. So hello guys, thank you for joining me for this session. And in this session, I will be explaining and giving you a tutorial on how to use multimodal explainable AI for medical imaging using Captum. Okay, so my name is Rachid Zeghlache. I hold a PhD in medical imaging and deep learning, and I'm specialized in disease progression using longitudinal and multimodal data. And today I'm going to show you why explainable AI is important in medicine and specifically in the context of multimodal data. So before we dive in, let me set some expectation for this session. So first, we will go through 3 examples, 1 classification example, 1 regression model, and 1 segmentation model. Both 3 models, 3 approach will be in multimodal approach that we're going to see. And the second thing is that all the data that will be used inside this tutorial is only based on synthetic data. Okay, but it's quite the same. The idea is that we have different modality. We have like clinical data, and we also have like ground truth that are meaningful based on the synthetic disease that was created. And the third thing is that everything can be run on CPU. Once you have downloaded the weights after the session, everything will be available on our GitHub and also on the RISE tutorial website. So you can download the notebook, the code, and also I will also push the data to either GitHub or Zalando for making sure that the data is open source. Okay, so all right, let's get started. So now let's go. We'll just like run the first few cells, but yeah, let's give like some fundamentals about explainable AI. So going to show like a comprehensive overview of like the explainable AI landscape. So this diagram introduces the core issue. On the top, so we have like deep learning neural network in black. In the side and the left side, we have like input CT. It can be a MRI, it can be a CT scan, anything. And in the other end, we have like the output. So it can be regression, classification, segmentation, anything, but it's producing like something meaningful based on the end. Okay. And once we have this, some clinician that want to, for example, use your model will probably be asking like why the model did predict this. Okay. And this is exactly like why explainable AI is used. So it's making sure that we understand what in the input was used and makes the output like understandable. Okay. So there is like the thing that you should not like. So there's 2 notions that are not the same. So interpretability and explainability are not the same. Interpretability, sorry, is like of a model is meaning that it's inherently like interpretable. For example, a linear regression or random forest. So for example, if you look at the features, you can understand how the decision was made. And in the regression, for example, linear regression, you can just look at the coefficient, and if certain feature increase for certain amounts, you'll see that the y output will increase, for example, with like the linear dependency. But in the other end, like when we want to apply explainable, it's when we do this after training. Okay, and it's what it's like, because saying in basically deep learning neural network black box. What we want to do is we want to make sure that we apply this post hoc method to like approximate what in particular inside the input, can be image, can be clinical data, it can be like both multiple images, in order to explain how the model behave directly. Okay, so that's the idea of explainable AI. So now let me give you an overview of like the importance. First, it's making sure that we can detect error when we are using like explainable AI. Can also build trust, because like if I'm building, for example, a model for clinician, I want to make sure that the clinician understand and is like putting his trust into the model, so it can give trust to the build trust for like using this. Third thing is like making sure that, for example, if you want to commercialize your model, you need to have like some certain type of compliance. And for example, FDA requires like explain the section if you want to like, for example, commercialize your model. And the last thing is that we often like forget to mention is that we can because we can like explain, try to understand what was like what in the input made the output like different. You can discover like biomarkers. So that's another like interesting thing about explainable AI. There's like three families of explainable AI. There's gradient-based that many use backpropagation, or those methods many use backpropagation. There's perturbation-based. So the idea is that you just like take the input, just like mask some region, or try to like perturb the input, and then you try to look like at the how this generate a new output, and then just to see if there is a big change. And based on this, you can have like some subtype of like different like importance map. And the last thing is attention based. In this tutorial, we will focus on gradient based and perturbation based. Okay. So let's dive deeper of like the different. Yeah, I mentioned this. Oh yeah, so I mentioned this. This is a bit of like a theory about this, and the idea is that for gradient-based method, the intuition is that we want to know which pixel, if we perturb slightly the input, what will change the model output is. And if you see like start to understand, just perturbing like a little image, it's like almost like taking the gradient. Okay, so that's the idea of like the back propagation. So that's why we are taking the gradient base are based on the back propagation, because they are based on the gradient. And the most like easy one is descendancy. So it's just like the gradient of the output with respect to the input. That's it. And we just take the templated, and we are done. There's like other type of gradient-based method, but they always use the gradient, and they try to have different type of way of calculating the gradient. And sometimes they take the gradient like on a path between like a baseline to the final image. Sometimes they try to like have like weights. For example, for the Captum, Captum, same. You have some weights inside, like they first select the layers, and then from this layer they calculate the gradient from, like, for example, for ResNet, there's like maybe the last layer where you have like, for example, a feature map of 8x8 or 17x17, and then we use this for the conventional feature, calculate the gradient with respect to this map. Okay, so this is we can come back to this at the end, but just to give you like a quick idea, the same goes for multimodal. So now this notation is for unimodal. The same goes for multimodal, and this is all it's done with the Captum API. So this equation, you will never be using this in your code. This is done directly by Captum API, and in the rest of this tutorial, we will only be using Captum, and I will be explaining to you like how to use it explicitly for multimodal use case. And this is like, if you need to understand like something clearly about Captum, is it's working like this. you have like a method, which is in our case like just integrated gradient dot attribute. Then you give the input. It can be a tuple, or it can be just a simple input. In our case, since it's multimodal, it's a tuple with two modalities. Then some methods are taking baselines, so we need to add those baselines. Most of the time, those baselines are like arrays with zeros or just a random vector with the same size of the input, and the target class, it's the index of the class that we want to inspect the explainable AI based on this class. That's it. Something also interesting is the modality importance. So since we do have those with this with the Captum API, we can get like the for example Captum integrated gradient, but can get some kind of feature importance that has the same size of the input. And then what we can do is we can calculate what we call the modality importance, which is a weighted sum of the attribute. And then in this tutorial, I will be showing you like how to do this. And it's basically a coefficient that based on the attribution that we calculated. Just say, yeah, for example, T1 was more important than T2 for example, classification or regression based on this simple example or over like whole data set. Okay. The second type of explainable AI family that we will see is the perturbation-based method. And the core intuition is want to see what happened to the model output when, for example, like I mentioned earlier, when we hide or change a part of the input. Okay, so this is not computing any gradient, and it's only relying on the logic and the probability from the model. Okay, and so this is model agnostic, and you can be you can use any model, but since we, for example, do a lot of like masking and changing the input, the actual method is way slower than the gradient based. Okay, there's like a couple of methods: occlusion, feature ablation, line, sharp. I'm sure you can like go to the API and see like not go into too much detail into like each method. Okay, and it is basically the same. So for example, we have like a feature ablation method dot attribute. We give the input. In our case, it's multimodal, so we give the tuple, and we can also give the feature mask. So for example, if you want like to mask with specific array, can be full of 1, full of 2. In this case, can be full of 0, or can be random. It's up to you like to choose what would be like the way to mask the input. Should be coherent and not like mess up with the actual value that are currently present inside the image. Okay, and also we have the attention base, but in this video we will this tutorial, so we will not like focus on those. Okay, just need to know that there is like those steps. Okay, so when you want to use like Captum, this is some kind of cheat sheet. You can come back later on when you use it on your own data set. And the idea is to have a PyTorch model. And inside the PyTorch model, there's two things that are absolutely important to have in order to make sure that the integrated gradient or any kind of method that you use will work correctly. First, you use a model that's inherits from nn.module. And you need to make sure that the signature of your forward function has all the modality that you use. So for example, if I'm using like a model with an image and clinical data, I need to make sure that I have the position for the argument image and tabular data. If, for example, I'm using like key args or args, it will like have a lot of issues later on. So you need to make sure that the signature for your model is representing all the modality that you use. Either way, it will not work. You will see that you will get like an issue with the forward. And for example, if you implemented a model and there is like the signature is not maybe you have used like a dictionary or keyargs or args, you can do like can add a wrapper. I will show you like how to do this and make sure that div wrapper is creating this forward function with the unfolded version with first modality, then the second modality. Okay. Also, something that you need to understand is the attribution map. Anything that is generated by Captum always have the same size as the input, always. So if we give like modality with centered shape, an image, or the second modality with like a centered tablet shape, the attribution, the feature importance, anything that you use with can be gradient based, attribution based, or even attribution based, will have the same size of the input. Okay. Second thing is this is all every time the actual use of Captum will look like. First, you have your model. You need to have it into like the device. Then you just use the integration, integrated gradient, for example, method that are from Captum. You pass your model. Then you make sure that you have your tuple. For example, it can be image plus tabular data in this case, but later on we'll see that we can apply this with image plus another image. You need to make sure that's also a very important thing is that these images need to have like need to have gradient. So they need to require gradient equal to. So if there is no gradient that is like that is recognized by PyTorch, this will not work. Cannot track the gradient, and it's based on the gradient that most of the gradient-based model methods are working. So you need to make sure that this is true. Then same for the baseline, we need to define those. And then we just calculate those attributes. And here, attributions is a tuple that has like the same size of the input. That's it. It's as simple as this. And then you can play with the baseline, and you can also play with the different arguments of the integrated gradient. So just go to the API, and you will see that sometimes there is a number of steps. There is sometimes some kind of sliding. There is kernels that you can change. So yeah, but the idea is always these steps, step by steps, and you will be able to use it like always, and you will always be able to like compute the gradient without error if you follow what I said before. So having this, make sure that you have your model that inherits from any module, and make sure that your forward is having two modalities, and then you follow this step, and then you are basically like ready to use Captum. For the output and the interpretation, most of the time, the interpretation is the following. If the attribution is positive, it means that the pixel or the output chosen is increasing the score. So it can be classification, regression, or segmentation. So it can just increase the logit. So we are like thinking in terms of the space of the logits. And if it's negative, so the attribution is negative, it means that it is decreasing the score. Okay, so it will just lower the logit, so it's going against the class that we are using. Okay, and if it's close to 0, it means that the pixel or the element inside the vector does not have any influence. Okay. The common thing that you should not forget when you're using like Captum are the following. So as I mentioned, you should always like make sure that your vectors that you use as inputs have like gradient inside tracked by PyTorch. So you can just like take your tensors and dot require grad true. That's it. Okay. Also, you need to make sure that you use the correct baselines. Okay, so you need to use meaningful references. So 0 can be mean black images, and those baseline should not be meaningful and mess up with the image. For example, if inside the image 0 is something that is important, having something else as baseline is a good idea. Okay. Also, you need to make sure that the target that you, for example, classification is an index. So we'll see this later. I will explain this in much more detail, but the target for the given class that we want to explain, the output of the model, what you give is just here, the attribution is just an index. So it's just 0, 1, 2, 3, 4, 5, depending on the number of class. If you are, for example, using regression, it's just 0 because it's just outputting like a single neuron. In the case of segmentation, we will see that we need to do some post-processing step to make sure that we are able to use this place ID, because in the segmentation, we are predicting like a segmentation map, and the class index is not similar to the classification. So to be able to use Captum post-segmentation, there is a step that we will see later, but you need to make sure that when you are placing the target, it is an index, can be 0, 1, 2, up to your class. And for regression, it's always 0. For classification, depending on the index of the class that you want to use. And for segmentation, it's same as the classification, but you need to add a small step that we will see later on. Okay. And for the best practices, most of the time it's good to like compare between Gaussian and perturbation-based method. Okay. It's, as I mentioned, use the appropriate baseline. You need also the visual properly. So most of the time, want to have like absolute value or normalize heatmaps. Okay. Also, you want to check with like the ground truth if like the result makes sense, because as you will see later on the tutorial, the results highly depend on the quality of the data that you trained, and also on your way of interpreting the knowledge expertise that you have. So always need to discuss. So if you do not have like the expertise, discuss with clinician or someone that is more like knowledgeable about the data set. Okay. And the last thing is always trying to work with, when you're working with multimodal data, you need to always try to understand which modality is like more like give more information for your problem. And you need to compute, like as I mentioned earlier, the weighted sum of the attribution. And this will give you like 2 scores, and this will like give you like what is the modality that is like more important for your given problem. Okay. So now just like repeating what I said earlier. So yeah, just remember that is the core API patterns, and also make sure to not forget those key principles. Now let's go to section 3. And what I'm gonna do now is just like make sure that I run all the cells. So let me go back and seeing if and yeah, perfect. So as you can see, I'm running on CPU, and you will be able to run this on your local machine once I like send you the link to download both the weights and the data. So let's run this. Perfect. Now we can run this, and now we're gonna talk about the data. Okay. So we have like 3 tasks. For each task, we have generated like synthetic data that kind of embed true ground truth signal. This is actually absolutely critical for validating the explainable methods. Okay, so let's work through each data set. So text for the task A, its classification. So we are using CT scan with 12 electronic health record feature to predict whether pulmonary nodule is benign or malignant. Okay, this is think of this like a lung cancer scanning scenario. Okay, for the input we have like one grayscale CT scan, 224 by 224 plus 12 feature including age, 5 years of smoking, SUV max from PET scan, nodule parameters, and other like clinical variable. But as I mentioned, this is not real data. It was generated. The script for generating this will be given inside the GitHub link of this session after we finish. And in this case, the target is binary, so benign was class 0, malignant class 4. Okay, so for the task B, it's regression. So we are combining, in this case, T1 weighted with T2 weighted MRI, brain scan to predict like continuous neurologic disability score. Can be like, think of this like for example, Alzheimer's. And the idea is to have like a ranging score from 0 to a certain like degree of severity. Okay, so the inputs are 2 MRIs, and the same. We are using the same size, so 224 by 224. And as I mentioned, the scalar here is a thing that I generated that is using like a data distribution that is skewed toward lower score to mimic like, for example, real MS cohorts where with like patient have like mild disease. Okay, and the task C, which is segmentation. This is the most complex task, which is using FLAIR and T1 control state and ends. So as I mentioned, everything is generated, and you will see that it is not as truthful that as I presented, but it's doing the job. And this is meant to be like for teaching purposes only, so you can easily like from your own data set, update the code and apply this to your, for example, own training loop, and just like take some part of the tutorial that I'm showing you now and just applying it in your pipeline. Okay. So for the segmentations, it's the same, FLAIR plus T1. And the idea is to have something that's, we have like, the target is like also binary, and it's for like, the idea is to segment part of the brain, and giving that, we just said that there is like a lesion inside the brain, and it's closely related to like, for example, the breast data challenge. Okay, so that's the idea of like the different data set that we have. And the rest is if locally you have like all the sets, you'll be able to see that this is the output. Since I already have like all the data sets, this is giving me this. But if you do not have, it will run the data set and create different number array that are representing like all the set plus the CSV that is containing both the clinical data and the labels. Okay, those are an helper function that we're using. Is this section is presenting like the different datasets. Dataset and pull that are loaded that we're using. It's quite common. So one dataset for the classification that is both loading an image, tabular data, and the label. Okay, so it's very classic. For the regression one, we are loading like T1 and T2 data, plus of course the score here, quite classic. And same thing with the segmentation dataset. We are loading both. F1 and the flare and the T1 plus the mask, and that's it. Quite straightforward. We are loading everything from the disk since the dataset is on my laptop. We are building the data loader, pretty much straightforward. And then from those datasets, we can then build data loader specifically useful for the explainable pipeline, and need to make sure that the batch size is 1. If you use a different batch size, you will see that if your laptop is like, if you have like a normal laptop, you see that you get like some issue of performance, and I think we'll get like starting to get issue, especially if you have a small GPU. So most of the time, choose like a batch size of 1 if you wanna for your explainable part. So we have like one dataset for training. So every, for example, it can be like train plus validation. And then we have like a separate dataset for the explainable AI. We could have used like the validation and the training, but it's more meaningful to have like the step on dataset data that were not used during training. Okay. So now let me give you like some kind of EDA about like the dataset that we'll be using. So it's always a good thing like to look at your dataset and make sure that you understand, and you start to like see the pictures, try to like, for example, forecast where should like your explainable AI method give you like insights. And also similar for the images or for the clinical data, you should look at the distribution. You should like, for example, expect that some, for example, clinical data should be much more important for your problem than other type of clinical data. And that should focus, for example, follow like clinical practice, and should be aligned with like, or like doctors are reading like the clinical features. Okay. So let me just run this. This is just for showing like the images so that we are generated. The CD here on the top row is like the benign image, and the malignant is just like almost the same images, but it's like kind of like a circle with like those straight line looking like a star. Okay. So if there is no star, there is no issue with the CT. If there is those kind of star, it's considered like with the disease. Okay. Then we can look at the distribution of the data, type of features. So there's all those features, 12 that will be used, and we can look at those distribution. Okay. But just go click on this, and you can look like after the tutorial. But yeah, it's all there with the distribution for each feature, age, everything like BMI, and so on and so forth. Same for the regression. We'll be showing you like all the data look like. So for the task B, for the regression, we have like T1 and T2. It's kind of, the fidelity is okay. It's not like, could have made those better, but yeah, you see the idea. And there's a score, okay? So for each, every image is like, there is the disease in every image, but the amount of the disease is proportionate to the score, okay? Then also can see the distribution of like the pixels, and all the T1 is the intensity inside T1 and T2 are correlated with the score. Okay, so since it's generated like the correlation is quite good, you like most of the time will not expect those kind of correlation inside a real world data set. And same for, let's see the data set for the segmentation. So yeah, as you can see, we have like the flare and the T1, and the idea is to consider this as like a tumor. side, so lesion, and we just created a current truth based on this. And the idea is will be like to then train those 3 models, but I've trained earlier those models. On your PC, if you do not use the .pt that I will be giving you after the session, and you try like to, for example, try for more time, try to, for example, play with the generated dataset, it will approximately take like, on my laptop, there I have like a GPU with 6 GB of RAM. So if you run this on Colab, it should not take like more than 1 hour. So yeah, you can basically like do the same on Colab, and I'll be showing you like the simple training loop after. So same, we have like some idea of distribution of pixels. In general, you should be looking at these parts more with more attention. But now, since we are like purpose of learning how to use Captum and how to apply Explainable AI in context of multimodal data, not like going into too much detail in this. But in real context and clinical data, this step should be like one of the most important steps. So you should always focus first on this, understand the data, look at the patterns if you find any, and then try to forecast what your explainable method will give, and try to make sense of the actual output from the explainable data. Okay? Okay, so now we have like a final cross summary data set that is basically like just giving us like the distribution of what the general case for task 1, giving us like the scores here, and same for the number of lesion area here. Okay. The task 1. So for the task 1, what we did is we used like a simple model. So we have some kind of small encoder here for the images, and then we have like some kind of feed-forward layer for the clinical data. So the EHR features, and then we conconnected those two. Then we have some kind of like classification head, and then we look at the object. Pretty straightforward, and the fusion classifier look like this. Okay, pretty straightforward. It's nothing complicated. As I mentioned, you always need to have your model generating from an module, because Captum is PyTorch based library. Actually, it was built by PyTorch team, and it's really focusing on the multimodal way of doing explainable AI. Then you need to make sure that inside your forward there is the 2 modality, image and tabular in my case. Perfect. And now, since I already have the CLS model.pt, since I've already trained this, I will not be training this in live. So since we already have this.pt, we just load the pre-trained weight. That's it. Then now what we do is, as I mentioned, we, for example, since we are in task 1, we use the CLS XAI loader with, since it's an iterator, we can use iter plus next, it will give us like 1 batch. And with this 1 batch, since it's batch size 1, we have like 1 image, 1 element of tabular data, and 1 label. As I mentioned, we need to make sure that the gradient is struct. So this is really important. You need to have like require grad true. And then what we do is we also import the model that we want to use. As I mentioned, there's multiple methods, and the most popular one, Captum, is interpretability gradient. We pass the model, so the class that we just defined here on top, and then we use like the object from this definition and dot attribute we we add like the inputs, which is tuple in our case because it's multimodal, as I mentioned, and also we add the baseline, we add the target, which is directly linked to the predicted classes. So here it's either 0 or 1. And as I mentioned, there is other type of parameters, so the number of steps in this case, and conversion of delta in this as is another parameters for this. Okay. So now we can look at the results, and as you can see, we get the feature importance for both the features, the tabular data, and the images. Here, as you can see, since the dataset and the model were not trained with longer epoch and the dataset is quite small, it's not that meaningful, except for the clinical data. It's like as it should be. So the age and the BMIs are like, I made sure that there were strong features for predicting the true class. But the idea is that here we have like the attribution map. And as I mentioned earlier, the more it's close to 1 here, the more important the pixel is with respect to the decision. So if, for example, those like pixels are quite red, some are yellow. And for example, in this case, it's class 0. And as you can see, everything was used, is considered for the prediction of class 0. Okay. We have like other methods. So in this case, deep lift. And as I mentioned earlier, these steps are always the same. We load the model, we give the model to the method, then use attribute. Same way, we follow the step that I mentioned at the beginning, and it will always work if we make sure that we have a model that inherits from NN module, and that inside the forward function, there is both modality, and then it will work without any issues. Same here, we have like, it's almost the same. Those two are gradient based, so as you can see, the distribution look kind of similar. Same for the feature based on the clinical data. We have like gradient, so value. Here it's, as you can see, it's not looking good. Sometimes you will see that when you apply your gradient based method, it gives you like weird result, and this is exactly where you want to dig and try to understand why the gradient was not giving you like a good result, or it's just giving you like a weird map with everything like, for example, highlighted. So it's not uncommon, and I use this example specifically because like when you will be using this for your own method, sometimes this will appear, and most of the time in space, this will appear if there is like an issue of gradient inside your model, or if the model was not trained enough. Okay. Same for now, we have like the breadcrumb. As I mentioned, the more yellow, the more attribution there is. Red is middle, and black is no attribution. And as you can see, there's quite, we have like some red dots and yellow for this one. That is just like giving, it's what the model is looking at much for predicting the class 0 in this case. So let's go for the other one and make sure that you can see, maybe go a little bit quicker, because like it's almost, we have like 20 minutes left for the tutorial, and I want to make sure that we have enough time for the questions. And okay, it's going both. Yeah, as I mentioned, the perturbation-based methods are taking much more time because they are like going through multiple forward steps, and just like masking the input multiple times and then producing this with producing this importance map with these multiple steps of masking. And as you can see, we get like similar like feature importance map with kind of a similar feature based. I think if the PCT was not found, yeah. So as you can see, we get like quite similar thing, but except for one feature, and this is also it can be like something interesting to have. And now we can ask like ourselves, why is this really important? And then we can start to, for example, ask clinician or just go to the literature and think about like the feature that we use and try to understand why it was so important inside the decision. Okay. Go for this one also. Should not take too much time, maybe like 15. Yeah. Okay, so now it's like a grid based for the malignant vs benign output. And as you can see, like the different, it's quite difficult to like very focus on like the actual thing that was added inside the image that is producing the actual disease. So it's not quite faithful in this example. So you cannot very differentiate or say, yeah, my model is concentrating on, for example, the small star. So now it's kind of blurry. And most of the time you will see those examples if you apply this inside for your own model. Okay. And the idea is to look at the gradient and also look at the just how much your model is faithful. It is also predicting just seeing the calibration is just looking at the IUC or, for example, the accuracy or something like just to a proxy of the performance of your model. Okay. So now let's go to text B, which is like multimodal regression, image plus image. You have T1, T2, and you have like two encoders. Then those encoders produce like latent representation. This latent representation is then concatenated, and then we have like some kind of like a classification head, except this one is regression head. Okay, quite common, very like usual for multimodal model, and it is same. We just load the model and just load the. And in this case, which is a bit better because the model was trained like I had like better performance for this. As you can see, for the, for example, little like lesion that we added, the contour is way yellow than the rest. So it's kind of like guessing what is most important inside the image. And here, as I mentioned earlier, we can compute like the importance in terms of classes. So in our case, T2 is way more important than T1 for this case. And to compute, it's pretty simple. What we do is just take the absolute value, take the mean of this, and then just look at the attempt, just to take the value inside the array. And then what we do is we just like compute the total to make sure that we have like the weighted sum, as I mentioned earlier. And then we have like this, give like some kind of score for the contribution. Okay. Quite easy to do. Same for another method. We can have like deep lift or CNC. Here, as you can see, it's kind of like looking at the red spot and actually having like the contour of like the lesion that was added. So it's, in this case, quite nice, but on the other hand, other methods, like as you can see, like for T2, it's kind of like all red everywhere. It's kind of difficult to see like if the model is concentrating on the right aspect. Same for those integrated gradient here with T2. So yeah, it's you have like the balance. You have like, for example, the dip lift with T1 is giving like correct estimate of what was important for the decision, but other model are like having some issue of differentiating the deletion. Okay, so let's just like go for this. We have like the same, can compute the same, and yeah, let's go a bit quicker. And this one, yeah, still integrated gradient. Is there like, yeah, it's still integrated gradient, so it should not take that much time. And then we'll go to task C with the segmentation, and I will be showing you the trick to make sure that you can apply the actual Captum Explainable AI layer to your segmentation model with the wrapper. Okay, so this is like a grid that just summarizes like what we discover, and it is basically what you want to have like inside your, for example, your report, your paper, to try to differentiate between different inputs and different methods. Okay, and then you should look at those and try to understand if the actual like output is meaningful based on knowledge expertise, underground truth, or any other information that is important for the disease. Okay. For the task C, it is also multimodal, and it is for segmentation. It is image plus image, and the idea is to predict a mask. Okay, it's quite like analog to FLAIR, and yeah, no, sorry, it's quite analog to Rust. It's inspired by Rust actually, and the idea is quite similar. Is we have like two encoder, and it's like a dual stream unit. So we have like one encoder for FLAIR, one T1. Then we have like a bottleneck fusion with like the latent representation of each modality. And then what we do is we upsample this representation to have like the predicted mask. Quite quite classic for this. And the model is here, okay? And as I mentioned, we have like always those two, FLAIR and T1, and we need to make sure that though is generating from an end dot module. We make sure that, yeah, there's nothing else to run. Perfect. Here, there is like training loop, which is quite common, very simple, straightforward training loop. Sorry, drink some water. And since I already have like a weight, it will not be trained, just load the current weight. And this is the part that is the most crucial for the segmentation. We need to add a wrapper of this model to make sure that inside the forward, what is outputted is something that look like a vector. Okay. So for example, if in our case, it will be just batch size plus just one value, but in the case of like multi-class segmentation, this will just look like a vector that look like the logit of a classification output. So to do this, what we do is we take the model, put it inside the initiator of your class. Then inside the forward, we use the model to produce the output. And inside, using the output, what we do is we just like take the mean of both dimension h and w, and this will create like a small vector. And this small vector can be indexed. And if we have multiple class, we just like index the given class that we want to use the explainable AI on. So that's it. And this is the most important thing that you need to remember for applying segmentation. So when you need to apply explainable AI, in multimodal setup for segmentation. This is you need to do this. The way it will not work, because as I mentioned, Captum is only working with index based on the output, and since an 1D index, sorry, and since the output of the segmentation is 2D, it will give us error and say that it cannot like do the differentiation on 2D space, something similar to this. Okay, so make sure to like for those that are interested in segmentation, make sure to like copy this somewhere else and save this for later. Then we have like the same ID. We load the data. We get like the two inputs. We use the interpreted gradient. And what we do is we construct our tuples, both for the input and the baseline. And we have like we add like the common parameters that we want to do. Same here. We can also calculate the contribution. We can like also do layer gradcam and choose a specific layer. In this case, we just choose like the last convolution layer. And as you can see, we have like both gradcam for flare and T1. And as I mentioned, for example, the first example for task 1, here the different attribution are kind of meaningful, but as I mentioned, since the model were not trained with long epoch and we did not do any data augmentation, and it was not any, I did not use anything fancy. The result that you can see here are not like what we usually would expect. So most of the time we'll not have like something very, very yellow here, and here we'll have like something like very dark to make sure that it only focuses on deletion and the rest is not taken. Okay. And as you can see, as I mentioned earlier, for attribution, there is positive one. So if it's like positive, it means that it's going in the same sense as the output class. So for example, if all of this is positive, and if it was for class 0, it means it was like all the pixels that were used for class 0, that affect class 0, and the negative one, which is in blue, are the one that are like decreasing the class, going like in the inverse of the class. Okay, opposite direction. You can do the same with other type, and we can make sure that we can normalize to make sure that you see those two. And what we can do is a technique that is often used is you will see that inside your attribution map, sometimes there is like too much value, there's too much noise, and what you can do is you just like add like a threshold to make sure that you can see like where are the value that are the highest, and if they are inside for example, a region of interest. In our case, if there is inside the lesion mask. Okay. So let's compute the rest, and as is quite similar, just using like different kind of techniques. Gradcam here for flare and T1. You can also use interpreted gradient. As you can see, all the steps are all the same, but we just need to make sure that we follow the right step to be able to use it. Okay. And this is, yeah, as I mentioned earlier, it's like a grid that is like basically like giving a representation of like the mask, the interpreted gradient based on the modality, and look at the ground truth and the predicted mask. The prediction are quite almost similar because like it is a toy data set, so it's quite easy to predict here. But usually when you're like working on your own data set in your like clinical with like a meaningful clinical use case, you will see that the result will diverge, and same for those maps. But the idea is always the same for your report or your paper. You always need to have some kind of similar figure with this grid size and having like one modality, the associated integrated gradient, for example, map, the other modality, and then the integrated map associated with this modality, and then having like the grand truth and the predicted mask to make sure that you see what was is there like a sense of what the model predicted, and try in order to try to try to have some correlation between what was predicted and what the attribution map are. Okay. Yeah. So before we wrap up the tutorial, I want to give you like a framework for evaluating your explainable AI quality algorithm. So you just like not just like generate the map and you got it done. You like have like you can take a step back and like have like this simple framework that is rigorous and validated like your explainable methods. Okay. And the idea is to always go for the first axis is faithfulness. And what does faithfulness mean is does the attribution actually reflect the model, what the model actually use? So it's to test faithfulness, you can remove like I attribution region from the input and check if the model confidence drops or not. If the attribution like says this region is important, then removing it doesn't change the output. And this means that the attribution is not faithful, and then the model is slightly linked. Okay. The second axis is plausibility. Does the attribution match the clinical knowledge? If you're radiologist or any kind of pathologist, say like the explainable method is highlighting a region that should not be here, for example, a spine on X-ray for pneumonia detection, that's obviously wrong. Okay, so you need to like make sure that this correlates with the domain expertise. Stability, what I mean by this is, so if we, for example, do small perturbation inside the image or the input, does this change a lot the predicted attribution map, breadcrumb, or integrated gradient map? If not, it means that it's very stable and that it's good. If not, you can just like see and try to understand why it's not stable. The other thing is look at, as I mentioned earlier, the cross modality between the different modalities that you use. For example, we computed like for all the example with images, the weights of the modality that were used inside the model, and try to understand if this is consistent with the actual clinical use case. Because we know for certain diseases that inside some modality you can see more clearly the lesion or the region of interest, and if this is aligned with the result, means that your model is good and the explainable AI worked correctly. On the other end, if it's completely reversed and the modality that should be most useful is not, it means that probably there is like maybe an issue inside your model, and you can, for example, try to retrain or look at the gradient and analyze more the results. Okay. And for the rest, I think, yeah, I did like some kind of explainable method comparison table. It's like a simple data frame that you can look at, and just for like having this in mind for the runtime, the stability, and the spatial resolution. And if it's using multi inputs. Okay. And I think that will be it, guys. So well, let's like wrap up the session that we had today. So we main takeaway that I wanna you guys to have is that Captum is focusing on gradient-based and attribution-based method, strong focus on PyTorch model and multimodal output. Okay, it's very important to look at the multimodal fusion analysis. You'll see that this is a lot of the time not used inside paper, but should be missed because is there something that I did not mention, but at the beginning. But usually, when you see like explainable AI inside the paper, it's only unimodal because most of the time people either way they do not know that they can use this in multimodal data, and when they does, they also forget like to mention that which type of modality was the most important inside the pipeline. And this is a very like strong indicator inside that you can use inside your clinical communication. Can be paper or anything related to like a report that is written. Okay. Three is like Captum proficiency. As I show you guys, it's always the same step. You just need to make sure that you follow the correct step, use the API correctly, you add like your the wrapper for the segmentation, make sure that you always do this, and you need to make sure that the forward function of your model do not use key args or args, because Captum need inside the signature of the function or the modality to be able to compute the gradient and to do like the forward pass for the prediction based methods. Okay, so that's it for the tutorial. Now we will go into the question section, and everything that I've presented you guys will be available shortly after the end of this tutorial inside our GitHub. Inside also the RISE tutorial website, where this notebook plus the link to a code for the generation pipeline of the data, and I will also be publishing the data set to Zolento. It's called like this, to make sure that anyone can download it and reproduce like this tutorial. And the idea is now is to make sure that you can apply this to your own data set. So the idea was quite simple, but now you can extend it to any kind of model that you want to use, and you can even extend like to 3 modalities. It's possible, and the idea is to have like strong knowledge now about this. So now you have like a strong background, and then you can extend. So now I'll be taking questions. So if you have like any questions, please write them down in the Q&A section, and then I will be like just answering those. So yeah, let's go for all the questions. First is Charles Lance. Although do you weight attributes AG if modality is much important? Modality is much more important. AG is much. Yeah. So as I mentioned, so let me maybe reshare my screen. The idea to do this. Where is the? Okay. Yeah. be able to see my screen now, and let me make sure that I have this window. Yeah. So to do this is quite simple. It is, let me show you. The idea is that you just compute the weighted sum of the attribution and do the sum basically. So it was somewhere, yeah, is somewhere here, same here, but let me show you like with the example that we mentioned, should be like pie charts, small pie charts. Okay. Okay, that's task 1A. So let me show the exact code. But the idea is just you take the sum of both attribution map, and then you make sure to sum along the both axes. So you get like just one value, and then you just like do weight and sum of those two values. But I'm sure it was somewhere, and now it's for weird reason. Yeah, super. So yeah, it's here. What is the importance? What you do is you take the attribution, the absolute value, take the mean of this, same for the second attribution, and then you do the sum, and then divide by for you take the first modality and then divide by the sum, and same for the second modality. Okay, hope it's clear. Good. So can get the notebook. Yeah, of course, you can get the notebook. As a surgeon and a very beginner in this course, you learning for me, I don't understand anything till now. Yeah, I think you need to have like some kind of background to understand everything that we have mentioned beforehand. And I advise you like to look at the different tutorial that we have inside or RISE tutorial code base, and it starts with basics. So you should like go there, and like you'll be able to have like meaningful resources for this. Okay. Question from Anis. Is the gradient-based method we are computing the gradient even for the input? If so, we compute the gradient with respect to what is different after applying the perturbation. So inside the perturbation-based method do not compute gradient, just like forward passes. That's it. And the for the gradient-based method, it's computing the gradient with respect to the output. Okay. And that's why we need to make sure that we add the class target inside the attribution map, the attribution like method for Captum. So here we go back. Yeah, it's taking with respect gradient output with respect to the input, and you need to make sure to always like have the target index, so it knows from which class it should take the gradient. Okay. Okay. Hope it's clear. Valentin, how well does Captum integrate with PyTorch Lightning? For instance, does it work with Lightning module instead of PyTorch and module? Very good question. I'm mainly using when I'm like building a module, I'm mainly using PyTorch Lightning, and it's working exactly the same, but you need to make sure that, as I mentioned earlier, you have inside your forward pass, uh, inside the signature of the forward pass or the modality. Because most of the time in PyTorch Lightning, what we do is we give like the full like key args, and we, for example, in the training step or validation step, we unfold the dictionary and we do the computation. If you do this, it will not work, and you need to make sure that the forward pass do have all the modality that are necessary for computing. Okay, where to work directly. Hi everyone, I'm not sure if it was shared before, but could anyone please share the notebook? Thank you so much. Yeah, it will be, everything will be shared. We shared inside the GitHub. I will be sending you an email. And this will also be available on the RISE tutorial website. So let me like give you like just the link. Let me GitHub. So if you go to GitHub and you type RISE, we'll be able to see like this. And you go to the organization, RISE-MICCAI. So let me copy and paste the actual. Okay. So let's go back. Yeah, just so this is the website, and all our notebook are available there. Okay. Okay, so yeah, we'll be sending all the code. So from question from Abindra, what are the square in the hexagon slightly right below center of images? Not sure if I understand correctly. What are yeah. Correct. Yeah, sometimes you get those because in perturbation based method, it is basically like using like squared to mask the images. And if your image are like a low resolution, which is my case, you will see that you get some kind of weird imprint inside the image. So you will see it, like the different like squared inside the attribution or feature importance map. And to like have this effect less, what you can do is either you can reduce the size of the mask, so it's an argument that you can give to the Captum API, or you can or you need to have like inputs that are way larger. So this effect is way reduced. Hope it's answered the question. Yet, what if you want to compare the attribution of each modality? If the image is more important than the data, can we just sum the attribution calculated by the sharp or depth lift of all pixels and get the whole image attribution? It's pretty much the same. Just need to make sure that when you do this, you need to make sure that you bring the attribution into the same size, same shape. Okay. So for the vector, it will be, for the clinical data, it will be a simple vector, but for the images, it will be first of the same size of the input. But the idea is to just sum all those features and then get like simple scalars. And then from scalars, you can do anything that you want. You can do like from scalar 1 divided by the sum, scalar 2 divided by the sum, and then that's it. You can do like everything like same for that I showed like for both images. Hope it's answered the question. Then what are your thoughts about using the training data as reference, especially for training action where you need the expected value? For this specific use case, indeed, it is quite common to use training set. And to like complement what I said earlier, most of the time it is good to use like explainable AI in validation of test set. But for if it's like your first time and you just want to test if things are working correctly, go for training first. And then what you can do is you can then use validation or test sets. That's the idea. Because if in validation, your explainable AI maps are completely mess, or you cannot like guess or make sense of what there is inside, there's an issue, and you do not even need to go to validation and train a test set. Okay. Hope it answered the question. Nova, could you please recommend some great paper, in your opinion, discussing AI completely? Actually, if you go to Captum, the website, inside the API, for each method, they point to each paper. So for this, we recommend the API is really well written, and there's like most of the time an explanation, theoretic background, and then they point to the paper. So it's a very good like source of information for this. Hope it answered the question. Okay. Where yes, yeah. But is there any advantage? So, and Kadesh, sorry for if I pronounce this wrongly, badly. If there is any advantage of explainable AI in medical imaging against a fundamental model? I'm not sure if I understand the question correctly, but those two things are not like similar. It's like XAI happen like at the end of your training, once you like have your model that have like good performance, and you wanna, as I mentioned, look at like what inside the input is making your model predicting given output. Okay, and a foundation model is by itself like weights, and you can use the weights as it is. You can fine tune it. You can like use it again. You can also apply explainable AI model, but it's like not directly. There is no against. It's like more complementary. So hope it's answering your question. Okay, perfect. So let's go back to yeah. So I have a paper on multimodal data, image plus tabular, light fusion, where I use RISE-MICCAI for the top performing table. Do you think I should choose correctly to keep the data separate in the end, or if there is any way I can keep the fusion in the explainability part of the study? I think yeah, it's pretty much standard to have like what you did, but I think it's could be a nice way to maybe do a focus maybe on each modality, because if you look at papers, there is like archetype. For example, if you look at a paper at like MICCAI or medical image analysis, there is always like explainable part at the end, and they follow the same structure. So having things different, and also giving motivation for having something different that, for example, is giving maybe a better message, or it's providing like better insights. I think it's definitely worth the shot for like trying to do something different. But doing the thing that you are doing as it is like common, and nothing is wrong about it. Hope it answered the question. Yeah, of course. Thank you for the great presentation, but I'm to leave now. So thanks, Jocelyn. Thank you so much for wonderful session. Thank you, Shah. Got it. Okay, perfect. And last question: if in your experience, how do clinicians interact with explainable AI? Are virtual maps explanation of to expert for expert diagnosis, or do they require additional numerical, rule-based, or textual explanation? This is a very good question. I think that it is explainable AI is by itself never enough. But for building trust, you need to have it. You need to like make sure that the clinician knows that the model is, even if the model is having like strong AUC, strong accuracy, in the head of the clinician, it will always be something that is cannot grasp even us. It's like difficult to understand like what are the mechanism that led to this output. And since medical imaging and healthcare in general is like a high stake problem, we need to like make sure to add any type of layers trust that we can add, and explainable AI is one of the layers that we can use. And we can also use like calibration, faithfulness, and the type of thing like this. But can you, as I mentioned, use like rule-based? But the idea is to, this is like some kind of like a tool, and this tool can be used with different other tool, and this will build trust at the end of the day. So this is very important. Okay, so I hope it's sorry, the question. I saw that you took the absolute value before getting the total feature attribution automatically. Why, if a modality that has positive and negative attribution that cancel out, wouldn't that mean that the modality is not credible for the prediction? So yeah, this is a very good question. I took the absolute modality for just the score. Okay, so the idea is just like for the score between the two modality, and for the normal maps, you should not take the absolute. Okay, so just for the score, because it's way easier. It can, of course, like lead to like minus plus sum, but at the end of the day, since you are doing this the same operation in like two variables, it's the same effect. So the effect disappear, and just look at the value that is produced by at the end. Okay. Hope it's answered the question. Thank you. Had wonderful tutorial explanation. Cannot wait to try. Good. Thank you for the session. Great. Thanks a lot. Okay. So if there is no more question, I think we can end this. And it was very good to have you guys. Wonderful. As I mentioned, everything will be in the GitHub and in the RISE-MICCAI tutorial page. And make sure like to share this with your colleagues if they are interested. Also, the live, this tutorial will be also available on YouTube on the MICCAI Society YouTube channel. So you'll be able to rewatch our tutorial now. And yeah, now it's up to you guys to take like different part of the tutorial and make it yours, and try it like into your own data set and your own methods. So that's it. Thank you guys for being here. And I think we can like say put a stop to the tutorial, and I'll be maybe seeing you in the other one, guys. Bye-bye.